Okay, so the main thing, just to recap yesterday's stuff, was learning what gravitational potential energy is. We symbolize it with U, but there's different types of potential energies. We're focusing on gravitational right now. Later today, we'll move into another type. But potential energy is stored energy and has the ability to release and in most cases do work on something when that release happens. But where this formula came from, as I showed yesterday, I'll hit it again real quick now. Potential energy for any object, I'll just use the same thing I was using yesterday, just the person on the skate park. So any object, as you get further away from some reference level, you gain gravitational potential energy. All right. Most of the time, we assume like the floor of like the room we're in or something, or out the ground outside is the reference level. Most of the time. But just watch when you're reading problems in case they define a reference level differently. Okay? We did 2 examples yesterday that both were similar. I went over throwing a baseball up, and basically when it was released, the problem told us to make the reference level your hand, the release point. And that just means that's where we measure all our y displacements from with that equation mgy. But then there was a second part to the problem. It was a separate example problem, but it was just a continuation where we looked at actually the throwing point. We were told to keep the reference level where we release the ball, but the ball doesn't magically fly up in the air, right? So you have to wind up to throw it at that point. So it is possible to have negative y values in that formula for gravitational potential energy. And the reason why it comes out negative is simply because of where we decided the reference point is. But also, keep in mind, and don't forget, this goes back to last chapter, once we have a value in joules, if it's positive or negative, that just represents gains or losses of energy in a system, okay? When it's some value in joules figured out by this stuff. But not to make it too complicated, basically potential energy in most cases is just pretty simple as far as the higher you go, the more you're going to have. All right, the further away from some reference level, the more you're going to have. And where that formula came from really was just an interpretation of work that we did in the past, which was, remember, work is F times displacement, right? Force times displacement. Well, we're talking about the work done by gravity as we lift something. If I'm lifting, gravity is doing work, but it's doing what kind of work? As I lift something up, the displacement, this goes to remember something from last chapter. The displacement is up, but gravity is always, the force of gravity is always down. And remember we said when work's being done by a force, if that force is in the completely opposite direction of the displacement, it's negative work. All right? So when we apply it to potential energy, though, it's not exactly the same thing, but it's almost. So if we plugged into the work equation of a displacement between y2 and y1, we could then make weight mg, right? And if I distribute, it just looks like this, and part of that formula looks a lot like this formula, right? Now, if y position, like going back to this guy, oh, I keep going back to the wrong one, sorry. If the y1 position is 0, the reference level, then that means the formula for the work done by gravity, this piece is gone, right? y1 0, and we have negative mg times the y we lifted to, which is related to this formula. It's just not negative anymore, all right? Which led us to a little statement here of how we could relate those two together. So it comes from the idea of gravitational work with the opposite sign, essentially, okay? But I don't want to get into it too more than that because I got into it in a little more detail yesterday. Just reviewing right now. Then other than knowing what potential energy due to gravity is, the other most important part was conserving energy. conservation of energy. And I am going to expand on this a little bit more. So energy is only conserved in a system as long as there's only conservative forces involved. And actually later in the chapter we'll define more deeply what it means by a conservative force. All right? But while dropping an object, let's take this person again. When I drop a person or an object, boom, energy is conserved as long as I ignore air resistance. Air resistance essentially is a form of friction, and friction is what we'll later define as a non-conservative force. Once we lose energy to friction, doing work on something, it's not easy to get it back. It's dang near impossible to contain it back. But gravity is a conservative force, because if something falls, and I have energy, potential energy right now, right? Gravitational potential energy, because I lifted this person up off a reference level, and I drop it, I could get that energy back by lifting that person back up again, right? That same amount to whatever level. Does that make sense? However, if significant air resistance is present, the work done by essentially the friction of it dissipates. Doesn't disappear, but dissipates. And it's not like you could grab it and get it back. Because we know friction, if there's enough of it, creates what? Heat. And heat dissipates into the air or other objects around it. It's not like you could grab that energy back in any kind of easy way whatsoever. So that's why the main reason why friction is a non-conservative force. So when we use the conservation of energy formula that says the total energy before should equal the total energy after, that's only for kinetic and potential energies. All right. Now it could vary. We could have different types of potential energies in there. So there was a term in the notes called mechanical energy. Sometimes it's referred to as total mechanical energy. The mechanical energy at any given moment of an object is its total of its kinetic and potential at that moment. Okay? So if I take this ball or any object and lift it up, right now it all has only what kind of energy? Potential due to gravity. So let's just imagine it falling in slow motion. I'm not actually going to stop it right here, but I'm going to hit pause right here. So it's actually moving through this point, okay? So now some of that potential turned to kinetic, all right? Because now it's in motion, right? For every joule we lose of potential, it turns into kinetic. That's why we say it's conserved. But if it's truly conserved and there's no outside non-conservative forces doing work on this system, then the total should stay the same. So let me make up a number. If we had 100 joules of potential to start, okay, and the object fell and started to drop, then we would still have a total of 100 here. It just would be divvied up differently. Some of it would be kinetic, some of it's still potential because we haven't reached the ground. When we reach the ground, not after it hits, but the moment it strikes, then it's all what kind? Kinetic. So if we had 100 here to start with, and if it all got conserved, then it had 100 when it hits. But the question is, then what happens when it hits? Where does it all go? So if I drop any object, just for Spencer at home, if I drop this person, okay, once we hit, then it seems like all that energy disappeared, right? Because everything comes to a stop, right? So at this point, we have non-conservative forces involved, which takes energy out of the system. So let's try to name them. What's some reasons why, this person doesn't bounce right back to where they were? All right. If anything falls, even if it's not very bouncy, from a pretty good height, it'll probably hit and rebound a little bit, right? This ball's not like a person. This ball's kind of bouncy, a lot. But some of that energy rebounds, right? However, if there was full conservation even after contact, what should happen? A ball should bounce where? Back to that height. It's nowhere close, is it? Or any object. So when it hits, there must be forces involved that are non-conservative, that are creating work being done that takes energy out of the system. Right? Otherwise, it would go back to there. Even if you get a really like super ball, bouncy ball kind of thing, which I don't know if I have one anymore. It's somewhat one. This is much more bouncy. It goes higher, but not even halfway back, does it, from where it's dropped? So even when you get something like, by the nature of its elasticity that's more bouncy, it still doesn't even make it close back. So somebody give me one thing that why, like, when it hits, any object hits, it doesn't bounce back to where it was.
Okay, some of the forces that important.
Okay, be specific. You're right. It hits the ground. But think deeper than that. What happens when something hits the ground? Let's take my bowling ball. Yes. Sound's one of them. Sound is a wave. It's what we call a mechanical wave. And all waves have one main purpose: to transfer energy. So if you hear a sound goes out through a medium, which the main medium is air around it, and transfers out all around. It eventually dissipates. Now's not the time to talk about why. But energy is lost out of the system is the main point. So one thing was sound. Another thing? Heat. Yes, and that one's, you might think, wait, there can't be much heat when something hits like that, but there actually, at the level of it hitting, there is. And some things, depending on the material and how hard they hit, create more than others. But just to prove it on some level, I'll take my two big ball bearings. I'm going to ask Sammy to hold this paper just like this vertically. Do that? Watch your fingers. Now look closely at that. Or even smell it a little bit. You smell that? Okay, what does it smell like? It smells like it's burning, right? If you look real close, that didn't break holes in the paper. It burnt holes in the paper. It's singed. So if you look real closely, you can tell that, and probably still smell it a little bit. All right. So now not everything makes that much heat. Two pieces of metal together, but it was enough to burn holes right through that paper. But the main point is, when anything hits and contacts something else, that shakes those particles up. And that creates heat. Very little in some cases, a lot more in other cases, but some no matter what. And heat is in some way kind of like the sound in the fact that it dissipates around into the air around it. So it doesn't stay in the system. So some energy is gone through sound, some energy goes away through heat. Anything else? Yeah. In that case, no. If it actually created like something that were like sparks were created or something like that, that's a possibility. But in most cases, not. But good guess. When I dropped that bowling ball, some of you felt it, if you were close. The vibrations, right? From particle to particle, right? And you could hear the sound of the desk vibrating, right? It creates sound, but on the particles hitting back and forth and within them and everything. So those are all reasons why once something strikes, we can't really use conservation of energy, at least not easily, to figure out anything past the point of once it hits. Conservation of energy is great for dropping something till it strikes, in that view, or throwing something up. Now, when I throw something up, we bring in, and I think we got a little bit into this yesterday in one of the examples, work other. Did I get to that, right? So, let me go to showing the formula again, though. All right. This formula right here is conservation of energy lost straight up with no outside non-conservative, like extra energy putting in, taken out, okay? So if we just take the 1s and 2 subscripts, just means some instance before and some instance later, all right, for the 1s and 2s. So in instance 1, or initially, whatever the total kinetic plus U gravitational is, should equal somewhere later in time this, as long as we're in a situation where everything's conserved. Okay? So, like again, a ball drop's a good one. Something like, as long as we take away friction on this person. Oh, this one friction's on, sorry. It's on the wrong one. Play it again. If I take away friction, this would go forever if you were this person. Same as like a swinging pendulum back and forth.
Could you just skate in one direction forever?
Well, if theoretically, if you had an infinitely flat surface, which doesn't exist, and you could take away all resistances, Newton's first law tells me things in motion want to stay in motion. Even if you just slightly pushed it, it would go on forever until something else interacted. Right? So actually, this does intertwine with Newton's laws still. Right? Remember last chapter at some point, I proved that the work-energy theorem, the fact that the total work equals change in kinetic energy, that theorem was actually built mathematically from Newton's second law and smushing in one of the kinematic equations with it. So it actually comes from all the same source of what we've been studying. It's just a different way to look at it. Okay? So, of course, this doesn't happen, right? Something like this is not going to go back and forth forever because we end up losing energy to factors that, even if we try to use, ball bearings to lower friction within the wheels, there's still, over time, friction, little by little, takes over. Even on a pendulum swinging back and forth. And it soon settles down, right? I discussed yesterday, this is the idea behind a traditional roller coaster. The highest hill is always which one? The first one. Because that's where all your energy comes from. You're dropped off that. A chain pulls you up in your cart. And it does work on you to get there, right? You don't magically get up there because work and energy all translate to one another. So work is done to get you up here, then it drops you, right? It drops you, and you have to, each subsequent hill, you have to still have enough energy to get up, all right? And you're losing a lot to friction. They try to reduce that. That's why steel rails and steel wheels are used. That has very low friction, but there's still a decent amount of friction. And that's why you'll never see a traditional roller coaster that has any hills or loops anywhere in it that's nearly as high as the first one. Now, I say traditional roller coaster because there's some out there that use like magnetic boosting to give you extra work pushed into the system. But once you're into that, we can account for it. But we got to tweak the formula. Once you're into significant friction or forces coming in and giving you a shove, essentially, adding energy in, it's not that we have to throw out the conservation of energy. We have to just account for that any other works if we can. All right? But like I said, for the case of dropping something, it's really hard to account for the energy losses. In the case of like sound and heat and things like that. So we could figure out how much it was total, but how it was divvied up is another trickier part. But anyways, when we did the height of a baseball example, when I went over that yesterday, we looked at it not when it was released, but a little bit further back. So there was something, the generic term is work other, we put into that formula, right? So I do work on this up to the release point, right? So that work I do is the work other. And we just need to correctly account for it, and it can work in this formula as well. So that kind of brings us up to speed to yesterday. And we'll work even more with work other right now. And what's really nice about this conservation formula, whether we have work other in it or not if necessary, is since energy and work are scalar quantities, it is a much easier way to handle curved path stuff. You might have remembered me in the videos yesterday saying that the ball example we did, the two examples on that. We could have actually, for what they are asking, what they gave us, we could have solved it with free fall and stuff we knew about it, and or in combination with straight up Newton's second law, right? But where it really is a nice place to use energy methods is when there's a curved path involved, where maybe the free fall kinematic equation wouldn't quite help me as easily, or it would be a lot trickier since we'd have to worry about breaking vectors into components. But since energy is not a vector, that's a non-factor. Okay? So, go to page, find 7.4 if you're not already there. Question, yeah? Oh, okay. 7.4. And I may have on my page, sorry. This is on page 209, I think. No, 210. Am I right there? I might have the number. Okay, actually, 209 is 7.4. Yeah, then 7.5. Okay, yeah, 209. Bottom of page 209. All right, so this is the first time. This is a good day for you guys to be back, because this is the first time your cousin Throckmorton is introduced. This is kind of a reoccurring character. Okay, everybody has a cousin Throckmorton, right? Your cousin Throckmorton skateboard. That sounds like a skateboard company. Okay. Anyway, skateboards from rest down a curved, frictionless ramp. If we treat Throcky, never knew that was short for Throckmorton, and a skateboard as a particle, he moves through a quarter circle with radius r equals 3.0 meters. Throcky and his skateboard have a total mass of 25 kilograms. Find his speed at the bottom of the ramp. All right, it does say it's frictionless, so it's kind of like a ramp like this. Okay, it's more circular than elliptical than this one is, but it's the same idea. So we're basically being released, and we want to find the speed down here, right? So as long as friction is ignored, we could just use the version of conservation of energy without any work other in it, right? If we're ignoring air resistance and friction. So if that's the case, what he should be at the bottom, without any outside non-conservative forces acting on him, will be the V that we're looking for. So he's dropped. So that means if you're dropped, what kind of energy do you only have to begin with in position 1? Oh, excuse me. Hello? I'm not there right now. No, I'm in my physics class right now. That's okay. But online study hall right now. All right, so where were we here? Okay, yeah. So we got this ramp, right? Like something like this. And if this is position 1, the drop point, we're calling position 1. What's the only kind of energy right now? Potential, right? And if we do calculate position 2 as the bottom, it all turns to what down there? Kinetic as it passes through that point, right? So as long as you have that basic idea down, it's pretty simple. Cancel out what we don't have, if any of them 0. Sometimes we might have situations where nothing's 0. There's a little bit of each. But whatever, the main idea is the total mechanical energy, as we call it, on each side should be equal to each other at any moment if there's no work others involved. So we plug in our formulas. The Y value, I know I stressed this yesterday in the video, but it's important. I just put in radius r specifically because that's what was given. That's the Y value. All right. It is the vertical height that we're dropped. All right. If you look at the picture, I thought they gave a picture in the book. Yeah, the picture's on the next page, 210. If you look at the picture, you could tell, since this is a circular ramp kind of track, where that person's dropped from is actually vertically 3 meters from the ground. because of being circular. They're like right here, like completely like horizontal, kind of to the center of the circle, right? And at the bottom, the radius would be 3 meters down. So any problem you use potential energy in, formula in, the y value, which in this case is the radius, is always measured vertically to the reference level. All right? So even if there's a curved track or a slanted ramp involved, you don't use the length of the ramp for the y value. All right? How far you are away. It's always a straight up vertical distance. And the main reason why is because, again, it's a scalar quantity. All right? That's what would make a problem like this harder in doing this in other methods. Because you might actually have to separate any vector quantities into components to figure it out correctly using some past methods. So this makes it very easy. All right, so we plug in these formulas. Mass cancels out. It doesn't always, but when it does, you could cancel it even if it gave you it. And we solve for the V2 position, which is at the bottom. We get about 7.67 meters per second. Will y'all get at that part? And they're going to mix something a little bit old, some circular motion stuff for what they're asking in part B. In part B, it says, find the normal force that acts on him at the bottom of the curve. Now here's where we got to use some old stuff, but going back to this. If we were just sitting there at the bottom still, and this person, what was this mass? 25 kilograms, so that's approximately 250 newtons, close, okay? So this person's 250 newtons. Just sitting there still at the bottom of the curve. What normal force will be acting on this person? 250 newtons, right? Or if this person is just skating, being pushed, skating, I guess it doesn't stay. So skating freely to the right or to the left, actually whether she's accelerating or not, the normal force would be what? 250. But be careful here. We got to think a little bit. Since we're on a curved ramp at the bottom, it's not going to be 250 as I pass through that point. Why? Why wouldn't it be? If it was in those other cases, and if we like paused it real quick at the bottom, it seems like the same situation, right? Not quite though. There's something happening in the circular motion down there. Remember when we did circular motion? What was the reason when something spun around? Even something like on a string. I think I lost everything in the last couple of weeks.
Oh, yeah, right. Friction on the-
Not friction. There's no friction still in this problem.
Oh,
Alright? But what makes you essentially want to fly off a turn? Big hint, it's not a force. Inertia. Alright? The property of, in this case, especially the mass in motion, right? So, since this mass is in motion through the curve, it wants to fly off the curve at any given moment. And basically, since the curve is right at the bottom at this point, as we pass through, it wants to fly off right there, creating essentially, like, as far as the floor of that, the bottom of that ramp is concerned, it feels heavier. All right? Is that person really heavier? No, but they feel heavier. All right? Just like if you, in a slightly different context, but still with circular motion, with circular motion, we talked about those rides like a roundup ride at Idlewild, right? Where once you start moving in a circle pretty fast, you feel heavier because, like, if you put a scale between your back and the surface behind you, that scale would read higher and higher the faster and faster you went, because you want to fly off, and flying off pushes you into it harder, meaning that the back of that ride has to push back on you harder, right? Similar thing, just a different arrangement is going on here, right when we pass through that point. So that's why we're going to solve this the way we're going to solve it, remembering that stuff. All right? So at that moment, the two forces we have, we're going to go back to Newton's second law. We can't do this part with energy, but we're going to use maybe some ideas, just variables from above. So applying uniform circular motion principles, Newton's second law tells us that for circular motion, that the force or forces that are affecting the circular motion at any given moment equals mass times centripetal acceleration, right? So we have normal force up on us and weight down on us at that moment. So we put that in as the net force, up positive, down negative, and we plug in to that formula. We know that centripetal acceleration is v squared over r. Now, I know I have the number figured out, but I solved it algebraically. We can plug in the number 767, but notice up here, if I don't go to plugging in numbers immediately, v2, this v, is the square root of 2gr, right? So if I plug that expression in for v2 and it's squared, that would just wipe out the square root, wouldn't it? Right? And that would be divided by radius from that old formula we know from circular motion, right? Hopefully you remember. That cancels out the radius, and that leaves us with just the mass times 2 times little g there. And we want to know the normal force, so we simply add over the weight, and it's 735 newtons. So remember, if this person was just sitting there at the bottom, never moving through circular motion, it would have been about 250, right? But because of the inertial effects of how those forces interact right there, it feels like more pressure right there. Does that make sense to everybody? Okay. Go ahead and take a break for a moment. Now we're just going to tweak the same situation we had, okay? It's hard to directly measure friction in some cases because of the fact of saying it's dissipated, and that means it would be hard to directly measure the force of friction. But by using conservation and knowing what would happen if there were no friction, because you might say, you know, why are we solving stuff like in the last example? Why are we bothering solving for something with no friction when a real situation would have definitely some friction, right? Well, to figure out how much friction there really was or is somewhere, we often have to figure out theoretically what something would do if there was none first, right? What would something do without it? That's what this number represented right here. This is how fast we would be at the bottom of that hill if there were no friction, right? But basically what the next problem tells us is, okay, now there's obviously significant friction in reality. And you could easily use a motion sensor at the bottom of this thing if you were setting up an experiment to find experimentally the velocity at the bottom, right? Or maybe have some kind of speedometer type thing attached to the person moving, right? The object moving. But this is saying it's now down to, it's only actually at 6 meters per second at the bottom of the hill because of friction. And then it ends up asking what work was done by the frictional force. Well, we could use the fact that what we knew without it with what we could find with it, and that velocity at the bottom. But now when we use the conservation of energy formula, we have to include work other. And that work other is going to be friction that they put in here. And remember, just as a look ahead, if we're solving for the work done by friction, friction always takes energy out of the system. So if we're ever solving for the work done by friction in this fashion for any situation, you better get out a negative number. Remember, it doesn't represent direction. A negative amount of work means energy lost from the system. And that makes sense because if we lose energy from the system, we wouldn't go as fast as we theoretically would have, right? So that's basically what's going on here. So we still have the fact that we're still dropping this person from that same height. So there's no kinetic energy to begin with. We just keep that work other for now, or you could write in work friction, since we know that's a specific type of work other we have going on. And at the bottom, we're still going to have all kinetic and no potential, right? As we pass through that point. So I solved some things in pieces, but you could plug it all in at once if you want. But, we could see, though, the reason why I solved it in pieces was just to really point something out. If there were no friction, since at the beginning, position 1, we have all potential, that means we started with 735, right? If we plug in the numbers for what our givens were. That would have been the same value as last problem. Because if we were just sitting there waiting to be dropped, friction hasn't acted yet, right? But then, in theory, this number should be what? Since it's all supposed to turn to that, it should be 735 as well, right? In the last problem, when we solved for the V at the bottom, that's what it gave us. That's what we assumed, because that's how we set up the equation. There was no work other involved. But we could clearly see, by solving for those, the before and the after total energies, that we lost a decent bit, right? So when we solve for work other, it just makes sense when you move stuff around, it just subtracts those numbers, right? But it is subtracted it in the order that it actually comes out negative, because work due to friction should be negative, like we said earlier, that takes energy out of the system, right? So, yeah, that's the last thing to say. Yeah. So does that make sense to everybody, what we did there? All right. One thing I want to say, it's not affected in this problem for the nature of it. But let's say they jumbled up this problem a little bit. And instead of finding the work due to friction being the work other, instead of finding it, what if they gave us the work done by friction? You got to be careful in that situation. If I said the work done by friction was 285 joules as a given, they might not tell you it's supposed to be negative. So if it's a given and you plug it into here, you got to make that minus 285 if they didn't already tell you that. Does that make sense? All right. If it's something you're solving for and you do it right, it'll naturally come out negative. But there is a chance you could run into a problem that says, here's the work due to friction. It's a certain value just to plug into that equation. And if they don't tell you it's negative, they need to. Now, all work others aren't negative, though. If I take this person and didn't just drop them, if I shove them, that didn't work out. All right. If I shoved them down the ramp, gave them a push at some point, that work other, if that was a given number, if I said I did push this person with 300 joules of work, that's work other, right? That's into the system. It wasn't like part of the system itself. That would be a positive amount I would plug in there for work other if it puts energy into the system, if I'm plugging in a number directly for it. Make sense? Okay. One more example, I think, with a couple parts, and then I assigned the problems yesterday. Like always, they're not due to the end of the chapter, which will be sometime later next week. So we'll finish out this section and this example, and tomorrow I'll post the video for all you guys of the next one. All right, 7.6, an inclined plane with friction. Now, versions of this problem I've seen many times on the AP test. Versions of, whether it be concepts or straight up math. So this is a pretty good one. We want to slide a 12 kilogram crate up a 2.5 meter long ramp inclined at 30 degrees. The worker, ignoring friction, calculates he could do this by giving an initial speed of 5 meters per second at the bottom and letting it go. But friction is not negligible. The crate slides only 1.6 meters up the ramp, stops, and slides back down. Part A, find the magnitude of the frictional force on the crate, assuming that this frictional force is constant. All right? So the setup equation, we'll get back to the givens here in a second. The setup equation, we have to use definitely work other involved, right? And that being of friction. So we're going to make position 1 basically the moment this guy let it go. Position 1 will not be as he's pushing, okay? It's once he lets it go. And it just starts up the ramp, giving it at the very bottom. If you let it go right there, right at that moment, we only have what kind of energy to start? Hint, it's at the bottom. It's at the bottom, but in motion. Kinetic, right? So that's position 1 right there. All right? So there's no gravitational potential, and we have to, for the time being, just put in work of friction right there as work other, right? That's what we're going to solve for. Well, we're going to solve for the force, but first we need to view it as the work. All right. Then it reaches some position, and we're going to have to figure out the vertical position of that. We'll get to the numbers in a second. But it reaches only 1.6 before it stops and comes back down, right? 1.6 along the ramp. But the main point right now isn't that number. It's the fact that it didn't make it to the top, and before it comes back down, it stops, right? Therefore, if it stops for a moment right there, we're going to call this position 2 right here. Therefore, we only have what kind of energy at position 2 at that brief moment? Potential. No kinetic since it stopped, right? So we could break down work of friction. Remember what work in general is. Force times what? Displacement, which we often last chapter called S for displacement. But if you want to call it D, I don't care. All right. So I subtract K1 to this side, broke up work of friction and force of friction times displacement, and I also divided over displacement at that time to isolate the force, right? But where we got to be careful is, I solved some of this separately up here. But it doesn't matter if you plug it all in at once there. But now let's look at the numbers we had. The mass of this thing was given. The initial velocity at position 1 was given. We know it stops at position 2. And we slid for this part of the problem 1.6 meters here. But we got to be careful. When finding the gravitational potential at position 2, one common mistake would be to plug in 1.6 there. But if you listened to me earlier and yesterday about what the Y value is in the potential energy formula, mgy, it's always the what displacement? All right, vertically. That's why we put a Y in there specifically to help you remember that. All right? So we weren't given that, but we were given the fact that we have a 30-degree incline. So 1.6 is essentially our hypotenuse. Just need a little SOHCAHTOA right there, right? And using the sine function and rearranging it to solve for this missing side, which would be the opposite side of 30, we would get out 0.8, 1.6 sine 30. Make sense? That's what we got to use for the Y value in calculating UG2. KE1, simple, 1/2 mv1 squared. V1 was 5. Mass was given. We could pop those in. I just transferred them down here and divided by that. Now be careful on this one. So we used 0.8 in the potential energy formula. But another place to go astray on this problem is accidentally use that 0.8 for this displacement, S. Where did that S come from? We divided it over. It came from the work of friction, right? Work of friction is force of friction times this displacement, right? Friction doesn't act along this axis, does it? No, friction does actually directly act along the incline that we're moving on, right? Make sense? So make sure for that displacement, S, we use 1.6. So just keep track of what you're doing and make sure you're thinking and not just plugging in numbers. Does that make sense to everybody? Any questions on that? All right. Once you do that, we get out negative 35 newtons. It did say just find the magnitude, though. So 35 newtons is fine. We okay with that one? All right, part B. How fast is the crate moving when it reaches back down to the bottom of the ramp? All right, let's just go from where we stopped it. It stops up here, right? At 1.6. So since we already called this point 0.1 and this 0.2, to be consistent, I'm just going to still call that 0.2, but this would be position 3, okay, when it comes back down. Now, this is another thing that this is a really simple question if there's no friction. If there's no friction, and you slide something up, when it comes back down to that same position, I think they said 5 meters per second, right? You let it go 5 meters per second. If there were no friction whatsoever, what should it be when it comes back down? 5 meters per second. That's a very similar idea to when we talked about free fall. Even though it's not free fall, it's still a similar idea. When I throw a ball up with 8 meters per second of velocity, when it comes back down to the position in which it was released, it would be that much if there was no other forces acting on it other than gravity, right? Same idea here. So just keep that in mind when solving. Theoretically, with no friction, at most it could be 5, right? This is, if you look for these little things and you solve for it and get over 5, you know you made a mistake, right? It couldn't be more because it wasn't pushed at any point, right? Friction is taking energy out of the system. That's the only other force that's there. So we got to expect to get less than 5. All right, so at position 2, which is this position, we again have no kinetic energy. And at the bottom, we have all kinetic energy, right? At position 3. When we get back down there. And UG, so everything's broken up like we did earlier. Now, we're going to use the force of friction from earlier because in the problem it did tell us that we're assuming the force of friction is constant. It's not varying. So we use the force of friction from earlier along the 1.6 meters, right? Because it's working along that ramp just on the way down. So we can figure out the work other directly. The work caused by friction is negative 56 joules. So we go to conservation and include that loss of energy for the work of friction in the work other. Up here I saw for the UG2 and KE. And the KET3 breaks down to 1/2 mv3 squared. V3 is what we want to find. When we solve it, rearrange, isolate, plug in the numbers. 2.5 meters per second, which should make sense. That doesn't guarantee we're right, but it makes sense, right? That's less than 5 meters per second because of friction. Any questions on that? All right, so those are all some pretty good examples, I think, to if you understand them, you should be all right with most of the problems here. Not all of them. All right, so if you didn't get started on the problems at all yesterday, get on it. If you kind of got started but not very far, use the rest of the time to work on this section. So, yeah, tomorrow's going to be section 2. Now, section 2 was a little bit introduced, some of it last chapter. You guys remember Hooke's Law and some stuff about work and springs? There was a couple examples on that. I don't think I put anything with that on the test, this past test. But there was some information in the chapter on that. You could definitely expect on the next test, nothing was on the last one, you're probably going to have something with Hooke's Law and elasticity. So I'll go over that in more detail. It was brief in last chapter to be focused on a little bit more in this one. The two main sections are today's and tomorrow's. All right, 7.1, 7.2. The rest are more, I would call, minor things. But something comes up called potential energy graphs in section 4, which, to be honest with you, before I taught AP Physics, it was probably one of those things in college you spent 2 minutes on. And like, I had to like look at it and learn either for the first time or relearn it because I didn't even remember. It's not that it's hard, but for whatever reason, they really like putting questions with it on the AP test. So we'll make sure. I'm going to go into it even though use some other resources other than your book because it makes like a little blurb of it and that's about it. But that may be later this week. It might not be until next week till we do that. And I think I'm possibly someday next week, even though Spencer's not here and he's by himself one day, we're going to probably try to do a lab. I'll be his partner. But I think that's what my plan is. We don't have too many double periods left. I still want to get other labs in.